Right then, so what we want to do today is we want to move on to looking at one of the most fundamentally important parts of being able to do chemistry, which is this idea about moles. Yesterday we started very, very basic and talked about what an atom is, what an element is. We talked about how you can write this thing called an electron configuration for any atom or any ion that we might give you. And we saw that the reason why some atoms want to gain or lose electrons to turn into ions in the first place is because they want to gain or lose electrons so as to end up with electron configurations that only have filled orbitals or happy orbitals, right? So fluorine goes to fluoride because the fluorine atom wants to gain an electron and so fill up all its orbitals. And then from talking about those formulas for ions and for atoms, we've talked about formulas of ionic compounds, and then at the end we got into talking about balanced chemical equations. Sort of simple, straightforward ones for the moment. They're going to get more complicated as we go on, but for the moment we're looking at the relatively straightforward ones. And so where we got to yesterday was talking about things like this. If we gave you a chemical equation that looks like this, H2 gas plus Cl2 gas gives 2 lots of HCl gas, then we saw that the balanced chemical equation, and we saw that that is balanced now because we have the same numbers of atoms on each side of the arrow. All the stuff that goes in is all there in the products, so you don't lose anything along the way. We said that 1 molecule of hydrogen gas reacts with 1 molecule of chlorine gas to give 2 molecules of hydrogen chloride gas. Right? That's the way that you should read that equation. And that's what the ones, which we don't write in, but are there in front of the H2 and the Cl2, and the 2 in front of the HCl are telling us. Right? They're about numbers of molecules. And so I kind of gave you these words yesterday. We say that the ratio of the molecules in this reaction is 1 to 1 to 2. Okay? 1 H2 reacts with 1 Cl2 to give 2 HCls. And so this is called the stoichiometry of the reaction. This ratio of these numbers, this 1 to 1 to 2, is what we call the stoichiometry. And we can determine the stoichiometry from the balanced chemical equation by looking at the big numbers in front of each of the molecules in the equation, which are called the stoichiometric coefficients. Right? And this is really important. In order to be able to do anything in the way of understanding or doing calculations about a chemical reaction, you have to first of all have the balanced chemical equation for that reaction, and so that means working out what these stoichiometric coefficients are, or working out what the ratios, the stoichiometry of the reaction is. Okay? Now, it is very important to understand and remember that these stoichiometric coefficients are talking about numbers of molecules or amounts of molecules. When we have an equation like this, it's telling us that 1 molecule of H2 reacts with 1 molecule of CO2. It's talking about numbers of molecules. So the stoichiometric coefficients are talking about numbers of stuff. It is not talking about masses. Right? So we do not read that equation and read it as 1 gram of H2 reacts with 1 gram of Cl2. Right? Even though, as we'll see, this is typically the way you would go about doing a reaction if you wanted to do it in the lab. You'd weigh stuff out. The stoichiometric coefficients are not talking about masses. They're talking about amounts, or if you like, numbers of molecules. Okay, and so to make that point, I have a slide about banana splits. It's one of my things. Used to be you could talk about banana splits at Govs, but I don't think Govs do banana splits anymore. Govs is not nearly... Do we know about Govs? You met Govs? Govs is a wee cafe up on George Street by the Knox Church, which used to be open until like 3 in the morning, all the time. Not anymore, never mind. But anyway, they used to be famous for their banana splits. So here's a slide about banana splits. And the point I'm trying to make here, and indeed there's a stoichiometry tutorial we do in 191 itself, where I actually put up a whole recipe for Anzac cookies or something. You can read chemical equations like reading recipes. Right? So, consider the following. If you want to make a banana split, then what a recipe might say is that you need 1 banana, and you need 3 scoops of ice cream, and you need 3 cherries. So 1 banana plus 3 scoops of ice cream plus 3 cherries enables you to make 1 banana split. Yeah? We're happy with that. Is anyone unhappy about the fact that 7 things make one thing? Yeah? And sometimes people get worried about that. And so you're happy if I said if you had 2 banana splits, how many bits of ice cream do you need? You're happy that that would be 6. Yeah? Obviously, you can't go and get a kilogram of bananas and 3 kilograms of ice cream and 3 kilograms of cherries and expect to make exactly 1 kilogram worth of banana splits. Yeah? That doesn't make any sense, hopefully, because that ratio of 1 to 3 to 3 is talking about amounts of stuff, not about masses of stuff. And the reason why, of course, it doesn't work for the masses is because the masses of the ingredients are different. Right? A kilogram of bananas corresponds to a lot more bananas, a lot less bananas than a kilogram of cherries would be. Yeah? So you can't do it by weight because the individual ingredients weigh different things. So you have to have the correct amounts of each of the ingredients in order to make a certain number of banana splits. And this is exactly the same idea when we're doing the chemical equations. Right? And so this is, it says this is the key to understanding stoichiometry and stoichiometric calculations. And this, again, like I say, is one of these things that fundamentally people never quite got, and they just try and pretend that it doesn't matter, and it really does. You have to understand this, or else somewhere on the line it all goes bad. Okay. So, stoichiometry and these big numbers are about numbers of stuff. And so up till now we've been talking about individual molecules reacting with each other. But there's a problem with that, and the problem is that by and large, because chemistry is a practical science and you want to be in the lab doing stuff, if you want to do a reaction to make a certain number of molecules, then you can't really go about counting out the number of reactant molecules that you want to use, because they're very small. And it's very difficult. I mean, it can kind of be done now, where you can actually do a reaction between individual atoms and individual molecules, but it's non-trivial. Right? You wouldn't want to do that routinely. And so working on being able to count individual molecules and atoms isn't really an option. And so chemists have developed another way of talking about it. And so the standard way of getting into this is to talk about eggs. And so we'll talk about eggs. When you go to the shop and you buy eggs, you tend to buy them in dozens. Yeah? You go and you buy a box of eggs, and you buy a dozen eggs or you buy a half dozen eggs. You don't tend to go and buy 12 eggs. Right? I mean, you do, but you don't go to the shop with the intention of buying 12 eggs. You go to buy a dozen eggs. Right? A dozen is a word that represents a certain number of things. In this case, 12. So you can have a dozen eggs, or you can have a dozen chickens, or you can have a dozen hedgehogs, or you can have a dozen buildings, or whatever. And assuming that English, you are happy with English, then you kind of know what that means. Right? A dozen is a word that represents 12 things. A pair would be another word. A pair is a word that represents 2 things. Unless it's a pair of trousers, but that's just complicating things. And then there's other words like gross. You may not come across gross. Gross is a word that represents, does anyone know? Anyone had fun holiday jobs in warehouses anywhere? No? A gross means 144 things, 12 dozen. So these are all words that represent a certain number of things. And dozen is the one that people know most often. And so it says if we say that we ate 12 dozen eggs for breakfast, then you would know what that means. You'd know that was bad, because that's a lot of eggs, because you know what 12 dozen means. Dozens, so then we could consider this chemical reaction. So here's a different one. Here's nickel metal reacting with oxygen gas to make nickel oxide. Okay, so if you like, that compound is composed of a nickel 2 plus cation and an O2 minus anion, if you like. Now what we talked about yesterday means that we could say this. We could say that 2 nickel atoms react with 1 oxygen molecule to make 2 molecules of nickel oxide. Right? That's what the stoichiometry of that equation tells you. So that would be fine, right? It's a balanced chemical equation, so what we're saying there is we're describing that equation in terms of numbers of atoms and molecules, so that would be correct. What we could equally do is we could say this: 24 nickel atoms react with 12 oxygen molecules to make 24 nickel oxide molecules. This would still be completely correct because we're still talking about amounts. Because a dozen represents a certain number of molecules or atoms. So long as the ratio is still correct, then this is still a perfectly valid way to describe the reaction. In dozens now, rather than individual molecules and atoms. Okay, so again, it's about the ratio of the different species, but it's the ratio of the amounts of them. Yeah? Okay. But of course, a dozen isn't really much use to us either, because 12 atoms are still a very difficult thing to count out compared to 1. And so what we do is we have this other thing, and this other thing, of course, is called the mole. And so the word mole is just like the word dozen. It is a word that represents a certain number of things. But the number of things that it represents is a much bigger number than 12. Right? The number is that number there. 602200000000000000000. So it's a lot. Or if you like, 6.022 times 10 to the power of 23. Hopefully, we are relatively relaxed about what's called scientific notation or standard notation, the 6.022 times 10 to the 23. If that's something which is new or is a bit of a worry, then make sure you stick your hand up in the tutorial and get some help with working that out. Yeah? It's really important. We're going to use numbers like that all the time. So this is a big number, and if you go Googling and you say, how big is a mole, then lots of people have come up with interesting and amusing ways of describing how big this number is. The one that I found that kind of seemed, well, I could kind of imagine, at least myself, is that if you imagine a marble, you know what a marble, a little round marble, 1 mole of marbles would cover the entire surface of the Earth 50 kilometers deep. That's quite big. If you have a stack of $1 notes and you have a mole of them, then that stack reaches from here to the sun and back. I mean, what was it? 800,000 times? It's a big number. If you have every person on the earth spending $1 billion a second, it will take them their lifetimes to spend it all. There's all these crazy big numbers. Anyway, there was a nice one about burying Los Angeles a kilometre deep in sand grains, but I can't remember. Do we have any Americans in the audience? I always like to check this in case, before I start slagging off on Americans, but we don't. Any Canadians? Well, they won't mind, but... Okay, so a mole is a really big number, and yet there is, if any of you are into these little green lift super energy drink can things, you know what I mean? Those little cans, the little green ones. They contain that many water molecules. Right? So one of those cans, in fact, it's got probably more than that many water molecules in each of those little cans. So that kind of gives you a feel for how small the molecules must be. Right? And yet, even then, you can actually these days count out individual molecules using crazy machines. That can be done now. It's pretty amazing. Hello.
Will we have to remember how much a mole is? How many molecules?
Probably not. We have a rule in first semester chemistry, which I think is still going to be the case, even though as the years go by I'm getting softer and softer on this. But the rule goes like this. We will give you every constant that you will ever need to know to do problems, but we won't give you any formulas. Right? That would count as a constant. It's a thing called Avogadro's constant. It's probably that may well say that on a later slide. And so we would normally tell you the Avogadro's constant equals 6.022 times 10 to the 23. if you needed it for a calculation. All right? But we wouldn't give you the formula into which you might need to put that number to work out the answer. So I don't think that you need to know the value of that. All right? This business about making you learn the formulas is the thing that I'm slowly getting a bit worn down on by the students year after year. We haven't had a decision about that yet. Maybe we'll change that for this year. But you can assume you need to know the formulas for bridging chemistry, though, because there's not very many. Okay? So, that is a huge number, but it's actually a convenient number of molecules for the sorts of sizes of amounts of stuff that we might want to use when we do experiments, right? That's how many atoms, how many carbon atoms there are in a sample of 12 grams of carbon. So you imagine a little lump of coal that weighs 12 grams, that wouldn't be very big. That would have that many carbon atoms in it, right? 18 mils of water has that many water molecules in it. 32 grams of sulfur has that many sulfur atoms in it, right? So it's kind of convenient size things. And indeed, that's why that number's chosen. It's kind of an arbitrary number because it's just a convenient number of atoms for the scale that you like to do reactions in. Yeah? So then, if we return again to our little chemical equation, which says that 2 nickels react with 1 oxygen to make 2 nickel oxides, now we can say, instead of talking about this in terms of individual atoms and molecules, or talking about it in terms of dozens of atoms and molecules, we can talk about it in terms of moles of atoms and molecules. And all these things are fine so long as we maintain this ratio, this one, in this case, this 2 to 1 to 2 ratio between the reactants and the products. So we can say 2 moles of nickel atoms react with 1 mole of oxygen gas to make 2 moles of nickel oxide. And if we do that, then it means that if we chose to, instead of writing the equation like that, write it like this, with a half in there, then that seems okay. Perhaps more so than writing half a molecule. Half a mole of molecules is okay because it's just 3 point something times 10 to the 23, right? You don't have to imagine chopping molecules in half to put them in your reaction. Okay? Right then, now we have to do some maths. The way we define the mole, if you were to look it up in a book and they said, how do we define a mole? You would say that the number of atoms in a mole of atoms is the same as the number of carbon atoms that there is in 12 grams of pure carbon-12 carbon. Right? Now, we talked about isotopes yesterday. And carbon, if you look at the number for carbon, you'll see it's 12.011. That means that almost all of the carbon in the universe has a relative atomic mass of 12, but then there's a little bit of the carbon which has bigger masses. So when you do that average, the average comes out as being slightly over 12. But the vast majority of all the carbon in the world has got 6 protons and 6 neutrons in it. And so that's the type we're talking about when we do this definition. So a mole is the same number as the number of carbon atoms that there are in 12 grams of the carbon-12 isotope. Right? So that's what it says there. Now, another way that we can say that is that there are 12 grams of carbon atoms per mole of carbon atoms. Yeah? And you might need to sort of read that through a few times to convince yourself that that's right. It's just another way of saying the same thing. Every mole of carbon atoms contains 12 grams. Every 12 grams of carbon atoms contains 1 mole of atoms. Yeah? It's just saying the same thing but round the other way. So if we can say that there's 12 grams of carbon atoms per mole of carbon atoms, then we can say that the mass of 1 mole of carbon atoms is 12 grams. And so this leads us to this idea of something called molar mass. The mass of 1 mole of that particular substance. And it's given a symbol big M, and I would normally make that big M italicized, but you obviously don't have to italicize it if you're handwriting. But the molar mass is going to be the mass of 1 mole of a particular element or molecule. And so we could say that the molar mass for carbon is 12 grams per mole. 12 grams of carbon per mole of carbon. Yeah? And so we could write it like this. 12 grams per mole, that little line there means per, just like kilometers per hour. You might write that. Or we could write it like this. And this is what you're going to see a lot more often, and if you haven't seen this way of doing it before, you'll need to get the hang of this, because this is the way we do it, pretty much exclusively in everything we're going to give you. 12 grams per mole. So the mole is written moles to the power of -1. Maybe this is a good moment just to do some algebra. If we write grams per mole like that, all in a single line, that is another way of writing it as grams divided by moles. So that and that are just two different ways of writing the same thing. And and so that's the same as grams times moles to the power of -1. And that's because if you have like just 1 over x, can I use x? I so don't want to make this a math lesson, but you kind of have to just get your head around this a little bit. 1 over x is another, it can also be written as x to the power of -1. As you go on, my standard thing is that if you can happily do like level 1 algebra, then chances are you're going to be fine for doing chemistry. You don't need level 3 calculus or anything to do first year chemistry. But little things like this, you do need to be very happy and comfortable about doing, right? So 1 over x squared is the same as x to the power of -2. These sorts of well, don't let me make you feel sad, but these sorts of simple things are really important that you can do comfortably. Okay, you're going to see this a lot. If this is something which is new and scary, then like I say, just grab the guys over in the tutorials and say, I don't get this. Or if I'm over there, just grab me and say, I don't get this. We'll talk you through it. Right? But we are going to kind of assume this sort of thing that you can do when we're just doing things like writing these units. So you need to be good with that. Yeah. Okay, so the molar mass then of carbon, big M, brackets, C, close brackets, equals 12 grams per mole. Now it turns out that this is the same, that the numbers that you get on your periodic table, which yesterday we called the relative atomic mass, also turn out to be the same as the molar masses, due to the way that everything's defined and set up. And so if you want to know the molar mass of carbon, then you just go look at the bottom number on the periodic table. And I am still getting you, I'm going to photocopy these this morning, so you'll all have one for your very own today, promise. And you will see it'll have 12.011, right? So that's the average molar mass of all the carbon atoms in the universe. And in the same way, the average molar mass of all the oxygen atoms in the universe is 16 grams per mole, and all the zirconiums is 91.22 grams per mole, and so on. So you can just look those up on your periodic table. You don't need to memorize them. Did we have to do this at school? Anyone? Well, that's something at least. You will get the hang of knowing that carbon is 12, and oxygen is 16, and hydrogen is 1. And maybe eventually, if you're lucky, arsenic's 74.92 and nickel's 58.71. But only because you're using that stuff all the time. And so it just sticks. You don't have to go home tonight and memorize them. I will not care. And normally, because these are like constants, we would give you them in an exam question anyway. We'll always give you a periodic table for your tests, but we might also give you those molar masses anyway. Because the point of the exercise is not testing your ability to memorize nonsense, it's to test your ability to understand how to use that stuff. Yeah?